So here's our show. It's kind of you alright there?
I'm trying to.
Yeah, right. So here we go. We're gonna. If anything goes wrong, I'm ready. But before that, kind of you alright there? And it's time that we look into the future, ladies and gentlemen. We're gonna look into space. The final frontier. Ladies and gentlemen, these are the monologues of the astrologer Pete Goldie to pontificate and explore the nether regions of gas and dust as it swirls, to justify the billions upon billions of dollars that NASA has spent, to bore you to tears with ridiculous bar graphs and charts. And ladies and gentlemen, here he is, Mr. Pete Goldie.
I'm here. Hi, chicken, I'm here.
Hi, Pete.
Hey, hi.
You think I'm gonna look at you? We don't do that.
Oh,
We look at the cameras.
Oh, okay.
It's show business, you know what I'm saying?
Got it.
This is the POV.
Well, look over here.
I can't look over
Well,
there.
look past me, behind me.
I'm losing my composure already.
The first picture we have here is a remarkable picture. It makes me uncomfortable.
Can we get this over with?
I think you'll be very excited when I tell you what it really is.
Whoa.
I doubt it.
This is the world's largest image of the Milky Way galaxy. But believe me, it's bigger.
Blinking.
No, we were telling you about that earlier. That's your projector. We're going to talk about that some other time. Remember, we have more than 30 seconds.
Really? That's my projector doing that?
We were starting to tell you about it earlier, and you said, let's talk about that when we have more than 30
Are you
seconds.
sure that the Milky Way isn't like blinking like vacancy? Vacancy.
That would be really scary, don't you think? It would be a problem.
What are we doing? What is...
No idea. No idea. Not part of my show.
Okay. If someone's honing in, elbowing in. I know, but when it comes to outer space, I mean, you can't do anything with a couple $100. What, for a couple $100, can they like buy like a space pencil or something?
Yes. The space pencil is exactly $100, as a matter of fact. You know that while you were in Europe, or should we say offshore of Europe, floating around on some junk, the Spitzer Space Telescope ran out of the liquid helium coolant inside its giant Dewar flask, keeping its sensors cooled to almost absolute zero, and it raised its temperature from minus 490 degrees to minus 400 degrees, where it is now. And 3 of the sensors in that spacecraft, of those 3, one of them no longer works because it is now a blazing minus 400 degrees Fahrenheit in that telescope. Still good enough to take 80,000 pictures of the center of our own Milky Way. Anyway, this illustration again is 120 feet long and 3 feet wide at its sides. It bulges right there in the middle, as you see, 6 feet tall. So it's actually, this is life-size representation, except you don't see it spanning 120 feet to the left and the right.
There's an arrow, which means that there's a fact there,
Yes,
right? Does that indicate facts?
Chicken, if you are as observant as I think you are, you will notice that there are 2 arrows, and they're lettered.
2 facts.
Yes,
fact
that's
A
right.
and fact B.
That's right. What we are looking at there are the youngest brown dwarfs ever observed. And again, you can only look in the infrared
Well,
because
they're pointing at the same fucking thing, though.
this phenomenon, which you're looking at, is called inferior projectitis. The youngest brown dwarf ever observed. You need infrared because it only glows and it's not even that hot. I think they only get up to 1,000 degrees. You know, you could probably get it hotter from a welding torch right here in Chez Poulet when you're making metal there. The hotter than that whole sun star dwarf thing it is.
Is there a brown dwarf joke that we can do? I knew it. I knew there was a brown dwarf joke coming. I could feel it.
We got it. Astronomers have now taken the first direct image of a planet-like object orbiting a star much like our own. But this one they're saying is different because the parent star is comparable to our own, even though it looks like some form of tie-dye there in the middle. What they're actually doing, it's a way in making the bright light of the star go away and just looks like tie-dye, so they can see these little things around there. And one of them, I think, is C question mark. I believe that's one of those they're a little worried about, C question mark. They think that might be a mass of 10 to 40 times that of Jupiter. And objects that are above 13 Jupiters are also considered to be brown dwarfs, very small brown dwarfs. So those little objects may not be planets, they may be in fact a small brown dwarf. Again, the Spitzer Space Telescope, 400 degrees below zero, still putting it out for everyone. This is the scheduled lecture. We're going to begin with the electromagnetic spectrum.
We're going to begin with Devo hats and belts.
Correct. And I want you all to follow along very closely here because we have to have a grip on the electromagnetic spectrum for me to explain what I want to explain now.
Is it on the quiz?
Yes, this will all be on the, all this material will be on the final. But I want to point out that this is the spectrum, we've all seen that, and the visible part of the spectrum is a very relatively small part in there, and you go from long wavelengths, low energy, low frequency, all the way up to short wavelengths, high frequency, high energy, and a small little area there. Now, I know you're fascinated with this, chicken, right?
Huh?
The visible light part of the spectrum is just a very small part. Where our visible telescopes with mirrors and lenses work is just this little area here and just a little bit below and a little bit above there.
Wow.
Yeah.
You mean all the rest of it could be porn and we wouldn't even know?
Exactly. You really are. The ultraviolet, they can barely pick that up if they use a good mirror with a very special coating. And then it gets up to X-rays. Now, I want to show you something about X-rays. Oh, I want to first explain that not all waves.
Wait a minute.
Well, you see, not all waves are easily blocked or easily reflected away. You see, not some of these, and that's again why.
Is the guy wearing tinfoil on his head?
Has problems with waves radiating out, and you know, if you don't understand how the waves work, you don't know how to block them. That's why I was showing you that spectrum earlier.
Is he gonna shoot the wave?
But let me tell you about X-rays. What this guy should worry more about than the visible.
Where did you find this guy?
Is
this guy close by?
It's blinking.
Is he gonna come in here now?
This is a Nobel laureate astronomer. He's well known in the astrophysical field there, and also a mass murderer. But anyway, the next image I want to show you is very important. It has to do with X-rays. Again, X-rays.
Anything goes wrong.
You see, you've got to
my
use
excuses. But
mirrors
before
that are concentric
questions and the answering and stuff like that.
Yes. First, you have to have a parabola, which bends the light barely in, then a hyperboloid cylinder that finally will focus that. And because you have to have these cylinders of mirrors to focus an X-ray, you get a 10-inch scale. But as you increase the energy of the electromagnetic spectrum, you can't bounce it off a mirror. You can glance it off at an X-ray. How do you detect the gamma rays directionally if they go through the gamma ray mirror like that and hit one of your cells and be absorbed and cause cancer? Now, how do you build a gamma ray telescope? That's what I want to talk about here. Now, first of all, they actually
do we have to build a gamma ray telescope? Why don't we just do something else? That's fun.
We got to do a gamma ray telescope. This is really important. The first gamma ray telescopes that they launched in outer space, and we were worried about them getting away with setting off nuclear bombs. And they knew, well, we have detectors which will pick up gamma rays, so if we put them in orbit, we'll know the Soviets are setting off nuclear bombs in space or in the atmosphere, and the radiation on the surface. We actually built these things up. They actually launched they put these up. Those actually man-made nuclear blasts which give off way out there 63,000 to 70,000 miles the first finding of gamma rays. Instead, they detected in space, gamma ray, top secret, and so scientists setting up a new go in and say, out there. And that's what they were taking out these gamma rays, and they were intended to be gamma rays, but there was gamma radiation flying through outer space. They didn't even know where they're coming from. They just started going off like a beep, and like, uh-oh, we got gamma rays. What do? Well, basically, you do something like a pinhole camera. where if you're lucky, your gamma ray will go through the tiny hole in the pinhole. You see, all you need to do is have a little hole, and the gamma ray will come through that little hole, and from that you can tell two angles of incidence and angles of scatter, and from that, if you're lucky and the gamma ray comes through and hits your detector, you know where the hole is, you know where the detector is, you can follow the line back and go, the gamma ray came from there. That's the whole problem, is you can't build a device with a tiny little hole and put it in outer space, because the chances of finding a gamma ray to get through that hole and then give you enough information is really, really small. So
why don't we do something else that's fun or interesting?
Yes.